In this video, we're going to be looking at factoring sums and differences of cubes. Excuse me. In the previous video, we looked at difference of squares. Now we're looking at sums and differences of cubes. Notice when we did difference of squares, it was just difference. It was just subtraction. This is actually the sum and the difference. So when we deal with cubes, which means to the third power, we can actually have addition and we can have subtraction. So let's look at how we factor sums and differences of cubes. Well, I'm going to give you the general formula for factoring each one. Let's look at the sum first. So for the sum of cubes, when you have two numbers that are both perfect cubes, remember we talked about perfect squares, like 4 is a perfect square because it's equal to 2 squared, and 9 is a perfect square because it's equal to 3 squared. Perfect cubes are numbers that have a perfect cube root, a whole number. 1 is a perfect cube because 1 cubed equals 1. 8 is a perfect cube because 2 cubed equals 8. 27 is a perfect cube because 3 cubed equals 27. So those are your perfect cubes. And so we want to look at perfect cubes and look for perfect cubes before we determine our factoring. Again, variables are perfect cubes. X cubed is a perfect cube. Y cubed is a perfect cube. B cubed is a perfect cube because their roots are all x, y, b. They're all whole numbers. So when we have a sum of cubes, your first factor is going to be a binomial that's basically your cube roots. So a is my cube root of a cubed, b is my cube root of b cubed. So that's your first factor. Your second factor is going to be your cube root squared, your second cube root squared, and then the product of the two cube roots in the middle. And when you look at this, the first factor is plus, it's addition, and then we have subtraction, addition. You're just going to be using this pattern to factor this out. I'm not going to go into the specifics of this and prove the factoring identity, the factoring structure. I'm just going to show it to you and show you how to apply it. That's all I'm doing in this video. I'm keeping it simple. So if you can see the pattern there, let's look at a sum of cubes. So let's look at number 1. Now number 1 is a sum of two cubes because I have x cubed. It is a sum, which means it's addition. Apologies there. And then I actually have 125. Now 125 is a perfect cube. It is actually 5 cubed. So this fits the format of a sum of cubes. So I'm going to apply this pattern to factor this sum of cubes. So this is going to actually equal, the first factor is the two cube roots. So x plus 5. The second factor is going to be the first cube root squared. So what is x squared? Well, it's x squared. The last piece is going to be the second cube root squared, b squared. So in this case, b is 5. So 5 squared is actually 25. And that's addition. And the center term is actually going to be the product of your two cube roots. So 5 times x, which is just 5x. And you're done. You've just applied the sum of cubes property. Let's do it again. Let's do number 2. So number 2, I'm going to be looking at the same thing. I've got a cubed. That's a perfect cube. I've got addition. And then I've got to look and see if 64 is a perfect cube. And 64 actually is a perfect cube. It is 4 cubed. So I can apply the factoring pattern, the factoring identity here for the sum of cubes. So my first factor is going to be my two cube roots, which are a and 4, added together. And then my trinomial factor, because each of these has a binomial and trinomial, is going to be my cube root squared, my first one, which is just a squared. My second one is going to be my second cube root squared. 4 times 4 is 16. And the middle term is the product of your two cube roots, which was going to be 4a. And you are finished. So that's how you do the sum of two cubes. Well, whereas you can't do this with squares, the sum of squares, you can do it with cubes. Now let's look at the difference of two cubes. And this is what we were doing that you can do with the squares. So now I'm going to look at the difference. So let's examine number 3. When you have the difference, and I'm going to write this up here for you, the difference of two cubes, difference meaning subtraction, you have a cubed minus b cubed. This is going to be very similar to the sum of cubes. In fact, almost identical, except instead of being a plus b, it's a minus b. And instead of being minus ab, it's going to be plus ab plus b squared. So when you do the difference of two cubes, if you look, the two key things, this sign and this sign switch places. Instead of a plus b, it is now a minus b. Instead of subtracting the product of the two cube roots, you're going to add the product of the two cube roots. So let's take a swing at this with number 3. I have my x cubed, I have my perfect cube, I have my difference, and then I want to see, do I have a perfect cube? Well, 64 is a perfect cube. It's 4 cubed. So I can, in fact, apply the identity here. So I have x minus 4, which is what we do with a difference. Remember, the only difference is my first factor is subtraction instead of addition. Okay? Then I'm going to have x squared, this cube root, 16, this cube root squared, and then instead of subtraction, I have addition in the middle. And I'm done. Again, look at the pattern. And I say identity. When you get into upper level math, you start looking at identities as two things that are equal to each other, or you can look at an identity as something that when we perform an operation, the identity doesn't change the value of the term or expression that you're looking at. We have additive identities and multiplicative identities, but that's more in set theory and when you get into advanced math, abstract algebra. But we're just going to call it identities here because it's two things that are equal to each other. You see it in trig with trig identities. When you say, for example, tangent is sine over cosine, that's a trig identity. But you're not going to get into that here until a little bit later. You should have seen some of the trig in geometry, but you haven't seen it expressed as an identity. You've just seen sine, cosine as tangent as related to the ratios of a triangle. So anyway, speaking of tangents, I'm going way off on one right now. So let's look at one more example of a difference of cubes. So for the difference of cubes, what if I have something like this and it's flipped? Well, it doesn't matter. You're still going to keep it in the same order. And I'm going to erase these perfect cubes over here so that I can kind of branch out. So I'm going to erase this here. So first thing is 125 a perfect cube? And the answer is yes. 125 is actually 5 cubed. So that is a cube. I've got my subtraction piece. And then x cubed is a perfect cube. So I'm ready to go. I can apply and I can plug into my pattern here, my identity. So my two cube roots are 5 and x. And since it's a difference, we got subtraction. There's nothing that says the variable has to come first. X cubed minus 5 cubed and 5 cubed minus x cubed are actually two different expressions. And there's no rule that says you can't have 5 cubed minus x cubed. You could also look at it as negative x cubed plus 5 cubed, but there's really no reason for us to do that in this setting because it would make it more difficult for us to factor. Sorry, I'm yawning and putting myself to sleep. So if we follow the difference of cubes, My first term is going to be this cube root squared, so it'll be 25. My last term is going to be this cube root squared, which is going to be x squared, and that's addition. And then I'm going to add the product of my two cube roots, 5 times x. So hopefully that helps you with the difference of two cubes, or the sum of two cubes. One thing to note, as in the AC method, and I should have addressed this in the difference of squares video as well, you do need to look and see if you can factor a greatest common factor out sometimes before you complete the factoring. So let me scroll up and see if I have one here. I do, but in the meantime, I'm going to do number 11 because I see that one and I think that one's important. That's a sum. That's the sum of cubes. So again, when you do the sum of cubes, this is your identity. A plus b, a squared minus ab plus b squared. So 8x cubed. Remember when we had the difference of squares, we're not always going to have a lead coefficient of 1. Well, 8 is actually 2 cubed. So I've got a perfect cube here. Plus 3 cubed. So what I'm going to do is I'm going to rewrite this as 2x cubed plus 3 cubed. Because I am, in fact, cubing 2x. 8 is 2 cubed. 2 cubed times x cubed. Laws of exponents. I can combine those and put them to the third power. So let's complete the factor. Well, the first one is going to be your 2 cube roots added together. What are my 2 cube roots? 2x and 3, right? The second factor is going to be your first cube root squared. Well, what's 2x squared? Well, that's 2x times 2x, which gives me 4x squared. My last term is going to be this cube root squared, 3 squared, which is 9. And my middle term is this times this, 3 times 2x, which will be 6x. And that is how you do that one. Again, it's the same principle as the difference of squares. If you've got a lead coefficient other than 1, you have to make it a cube. Now, if these aren't able, if you cannot make these and transform these into cubes, if they're not perfect cubes, guess what? Not factorable. They're not factorable. So let's look at something like number 14, and this will be the last example. Number 14 can be kind of a booger. Again, we have nasty, large numbers. So the question is, can I factor anything out of these to make these smaller? I want to make them smaller so that I don't have such, yawning, large numbers. I'm putting you to sleep too. So let's try, first of all, even numbers. They're both even. So let's factor out a 2. That gives me 125 x to the 4th plus 64x. Okay, well, I took care of the constants. And what does this do for me? Well, 250 is not a perfect cube, but when I factor out a 2, 125 is a perfect cube, and so is 64. But I still have this problem, x to the 4th. Well, let's factor out our common factors. Well, I factored a 2 out already. Well, both of these guys have an x, so I can factor out an x as well. That leaves me with 125x cubed plus 64. Now I've got a sum of cubes inside the parentheses. Just like I showed you with the AC method, always look for greatest common factors first, pull those out, then factor. So I've got 2x. And I'm going to rewrite this as 5 cubed x cubed plus 4 cubed. You can see how this is kind of coming together. Well, I can further write that as 2x times 5x cubed plus 4 cubed. Now we need to look at the formula that we have for factoring a sum of cubes. So when we do this, you can see what we've created here by factoring out again the GCF 2x. So now I'm going to use the framework for factoring a sum of cubes. And this is a sum because it is adding two cubes together. So the sum of two cubes, when we add two values that are cubed, that are perfect cubes, this is the way we factor. So looking at what we have A and B, the two quantities cubed. The first factor, when it's a sum, is going to be A plus B. So in our case, it'll be 5x plus 4. Now, the only difference between a sum of cubes and a difference of cubes, just to give you a reference, is remember if I do A cubed minus B cubed, the framework pretty much stays the same except you have a couple of sign changes. And that's the addition and subtraction pieces in the trinomial part and the binomial part component, the factors switch. So whatever you have here, that is your lead sign. That is your lead operation. So if it's a sum of cubes, your lead operation is addition, and then the second operation, which is the first one in the trinomial factor, is subtraction. So if it's a subtraction or a difference of cubes, the lead operation would be the subtraction piece, and then in the trinomial, your lead operation would be addition. So that's the only difference between the two. However, we're looking at a sum, so let's factor this out. So I'm going to have my 2x, because that doesn't leave. I've got to keep that and maintain that. And my first factor is going to be my two bases here, A and B. So I have 5x plus 4. Because my two bases, my two cubed values are the quantity 5x and the quantity 4. So then I'm going to come over to the second factor, which is the trinomial, and I have a squared. So that's going to be the base squared for my first one, which is 5x. And 5x squared is 25x squared. Again, where did I get that? Well, I took 5x and I squared it because we're squaring the first term. And when I square 5x squared, that's the same thing as 5x times 5x, which is 25 times x squared. The other way to look at this is with your power rule for your exponents. That's the same thing as 5 to the second power times x to the second power. Both are going to get you to the same spot and the same end result. So I have 25x squared. The next component is the product of our two bases with the subtraction operation. So I'm going to multiply 5x times 4 because 5x and 4 are my A and B term. And that's going to give me 20x. So this is going to be minus 20x. And then my last piece, and my pen is messing up a little bit here. My last piece is going to be adding the second base squared, which is 4. 4 squared is 16. So this is our final factored form for this particular sum of cubes. And don't hate on my beautiful box there. So this is what you will do if you don't see the cubes right off the bat. However, you always, when you look at factoring any kind of expression, you always want to see if you can pull your GCF, your greatest common factors, out first, because that usually creates an opportunity for you to simplify and deal with things that are a little bit more, a little less complex when you're trying to actually figure it out and break it down. So that is the sum and difference of cubes.